All right. Now it's working. All right, so we're on part E. I'll try to go a little bit faster here. At t equals 3 seconds, is the speed increasing or decreasing? That is kind of like what we did in the warm-up. Speed is different than velocity, so what do we need to look at again? Velocity and acceleration. So I'm going to say we need v of 3 and we need v prime of 3, which I'll go ahead and call a of 3. We need to compare those. So do we have the velocity function anywhere? Yeah, we have that up here, right? It's 2t minus 4. So if I plug in a 3 there, I get 6 minus 4, which is 2. And as we said in the warm-up, you can go ahead and say that's greater than 0 right there. And then a of 3, we found up above, it was always 2. So that also equals 2, which is also greater than 0. So if you have both of the inequalities there, then you could just say, so speed is increasing. Speed is increasing at t equals 3 seconds. There you go. Why are they increasing? Because the velocity is to the right and the acceleration is also to the right. They are working together. Speed is increasing. So that's how we say it. Speed increasing, speed decreasing. We don't say speeding up and slowing down. We also say acceleration is positive and acceleration is negative. So we don't say like decelerate. We don't say that. All right, part F. During what times is the particle moving to the left and to the right, and where does it change directions? So what are we going to analyze that, or what are we going to analyze here to determine that? Velocity. Good. So let's come back up here, grab the velocity equation. I have it right there. It's already labeled as v. So we'll come down here and we'll hit paste. Now this velocity function is of course a polynomial, so it is continuous everywhere, yeah? And therefore, in order for the sign of this function to change, it must pass through what number? 0. So the first thing I'll do here is I'll set it equal to 0, and then I'll solve, and I get t equals 2 seconds. Now we need to figure out if the velocity actually changes signs there, and if it does, how does the sign change? Well, there's a couple ways to do that, right? Probably the easiest way is just thinking about what the graph of velocity looks like. It has a slope of 2 and a y-intercept of -4. And remember, we're only using this equation for values of t greater than or equal to 0. So the y-intercept is a negative number, and then it goes up at a positive slope, which means at 2 it must change from what to what? What sign to what sign? Negative to positive, right. So if you wanted to like sketch that over here, v of t, there's t, so here's -4, and it looks something like that. And we just found this value here to be 2. So we could say something like this. Particle is moving, let's do left first. Left on what interval? -infinity to 2? Yeah, this is where you got to be careful. So on any free response, if they give you something like this, it's probably for a reason, meaning you're probably going to have to be aware of that later on. So we don't want to say -infinity to 2, but starting at 0, right? Would we want to include 0 in this one? Yes, because what's the sign of the velocity at 0? It's negative. So you say it's moving to the left on, and then you could just say t epsilon if you want, and you could say beefy bracket 0 up to 2 parentheses seconds, comma, we'll add moving right on what interval? T epsilon everywhere to the right of 2, yeah? So from 2 to infinity seconds. So of course you're also welcome to use inequalities. The top one would be 0 less than or equal to 2 less than 2 seconds, and the bottom one would just be t greater than 2 seconds. But even right there on intervals, you want to go ahead and put your units, and then we'll go ahead and just add here and changes directions. Particle changes directions at t equals 2 seconds. And then the reason would be since or because. And what would it be? Since it, or since the graph, or since the function? Do any of those work? It, the graph, the function? Is it because it's 0 that it changes directions? No. Remember, in general, it doesn't have to, but it's since v of t changes the graph of the function, or just v of t changes from negative to positive, not in France, but also at t equals 2 seconds. That's the kind of sentence you'll get really used to saying, because when we do something later on called the first derivative test, it pretty much follows that exact same template. Here, at this value of t, is where this behavior happens, because that also happens to be the same location where the function changes sign in this particular manner. Okay? So the particle changes directions at t equals 2 seconds, since v of t changes from negative to positive at t equals 2. And of course, when we say negative to positive, we know that we're reading it from left to right. That's always implied. So the y values are negative immediately to the left and positive immediately to the right. So that's the thing that I mentioned in the warm-up, where on the exam you have to not only say that there is a sign change, but really for it to change directions, it shouldn't matter how the sign changes, but you do need to say how the sign changes. Additionally, we could infer from here pretty easily that it did change directions and went from what, left to right or right to left? If the velocity changed, it went from left to right. Yeah, we're on a horizontal line, so when your velocity is negative, your positions are decreasing, getting smaller, so we're moving to the left. And if your velocity is positive, it's moving to the right. But we don't even have to say that. We don't even have to say that. So that's the justification. Whenever it says justify, it's going to involve some type of mathematical argument. And in this case, it's just v of t changes from negative to positive at that point. Do we need to say that twice? Do we need to say at t equals 2 seconds and at t equals 2 seconds again? Do we need to say that twice? The answer is yes, okay? You're saying here is where the change in direction happens, because that also happens to be the same place where the sign of v changes in that manner. Now, if you want to use a pronoun here, that's a clearly defined antecedent. At t equals 2 seconds, since v of t changes from negative to positive at this time. Okay? This being the pronoun, referring right back to there. That's fine. But it's almost easier just to say at t equals 2 seconds again. Okay? Contribute. Kind of put a little outlay here. You're getting Bob Ross inspired is what you're doing, right? Yeah. Find the total distance the particle travels during the first 3 seconds. Okay, so total distance traveled. Is that the same as displacement? No. Is it ever the same as displacement? It could be. Under what circumstances? No change in direction. And also traveling in which direction? Positive, to the right. Or if we're in a vertical line, up. Yeah, because if I'm moving in one direction, we're not going to change sign. But if I'm moving to the left, my displacement will end up being negative. So only if we're moving in the positive direction. I went 4 steps to, well, that's my right, y'all's left. I went 4 steps to y'all's right, and I'm displaced 4 units, okay? But in general, it's not. So how do we find it? Well, we come back up here. It says that the total distance traveled, it's up here somewhere. Oh, thank you. Yeah, golly. Distance traveled. Distance traveled is the sum of the absolute values of the distances traveled, or the displacements between turning points. All right, so we need to know where it turned around. Do we know where it turned around? At 2, right? So if you want to do it blindly without the graph, which we'll come back and do the graph here in a second, we'll just call it distance equals. It's the absolute value of the displacement between turning points. So it says during the first 3 seconds. So I know it turned around at 2. So it's going to be x of 2 minus x of 0. I started at 0. I know it turned around at 2. Plus, then the displacement's absolute value from 2 to 3. So that'll be x sub 3 minus x sub 2. Now, in this case, it doesn't really matter if you're subtracting correctly, but it's probably a good habit just to get into to do still right minus left because it's still displacement. So it's the absolute value, the sum of the absolute values of displacements between turning points. So let's go ahead and now calculate it. X sub 2 minus x sub 0. We'll plug it in up here. X sub 2, we haven't even found that yet. That's going to be 4 minus 8 is negative 4 plus 3 is negative 1. And then minus x of 0 is 3. So if you notice, that displacement is negative 4, which means in the first 2 seconds, it went to the left 4 units, which we kind of already know it was moving to the left when we started. We found that earlier. Plus x of 3, we still have that from up above. That was, we never calculated. That was 0, right? 0? Yeah, it is 0. Okay, cool. That's 0. And then minus x of 2 is still 3. No, it's negative 3. It's a 1. It's 1. Negative 1. It's negative 1. Yeah, this is where tunnel vision really gets me, having to scroll up and scroll down. Because to go with that tunnel vision, I also have a really horrible short-term memory. But, you know, if you have a paper in front of you, it's a lot easier. Yeah, so let me just verify one more time. X of 2 is 4 minus 8 is negative 4 plus 3 is negative 1. Yeah, so if you notice, that displacement without the absolute values is positive 1. So you can kind of tell the story here very basically. It went to the left 4 units, and then it turned around and came to the right 1 more units. All right, so left 4, right 3 is a displacement of negative 3. But what's the total distance it traveled to do that? 4 plus 1 is 5. It traveled 5 total units to net 3 to the left. All right, so that's how you find distance traveled from the position function. Now, if you wanted to actually come way back up here and sketch the original one, you know, that can kind of inform your decision. Does this thing factor? Minus 3, t minus 3, t minus 1. So to sketch that, we've already sketched the velocity function, but this could be the position in feet against time in seconds. And it has an x-intercept at 1. And then at 3. And the y-intercept was also 3. So it looks something like this. And now, again, because it's a parabola, you can figure out the x-coordinate of the vertex because it's always going to be the midpoint of your x-intercepts. So how do we find a midpoint of two numbers? Let's review that. Yeah, add them, divide by 2. It's their average. So 3 plus 1 is 4. Half of that is 2. So there's 1, 2, 3. So it comes in like this. I'm not sure how low it goes right there, but then it comes back up and does that. And so if we want to figure out kind of the story now, we can now see that because the slopes are negative from 0 to 2, the particle's moving to the left for the first 2 seconds. There's a horizontal tangent line at 2, so that's where the velocity is 0, and then the slopes are positive to the right, so that's where the position is increasing again. So if we wanted to figure out the total distance traveled from 0 to 3, we would need to figure out this distance here, which is what we found. And then we would need to figure out this distance here, which is what we found, and then add them together, okay? So you could also graph it to kind of help make sense of the problem, but really we want to try and get in the habit for equations like this, just kind of doing them blindly. All right, so there is your first full-length particle motion problem. You're given the position equation, and we could find all those things from there. Now, if this were a free response question, you wouldn't be asked quite all of these things, right? But any of these things could be asked, so we prepare for all of them. All right, any other comments on this one? Particle. Maybe it's fun to name the particle before we start. Kind of personalize the problem a little bit. All right, example 7. The graph above shows the position, y of t, of a particle in inches now, moving along a vertical line from t equals 0 to 7 seconds. So again, we're on unit alert. We have inches and seconds now instead of feet per second. We're moving on a vertical line now, so notice the position is not x of t, but y of t. So positive velocities are going to be up, negative velocities are down. And the other noticeable difference about this one is, instead of an equation for position, we're given a giraffe, right? Which here would be one leg, and then here would be, right, a giraffe. Or a giraffe, just a graph. Yeah, just a graph. All right, so we could answer the same types of questions from a graph instead of an equation. Let's do this together. On what open intervals, so no beefy brackets, from 0 to 7, so not including the endpoints, is the particle moving down? Justify. Particle moving down, particle moving down. So what are we looking for? Negative velocity, good. So give yourself something to work with. We want to know where the velocity is less than 0. Now from a graph of position, if I want to know what the velocities are, I'm looking at the what of this graph? Slopes, okay, the y values of the positions. And this is just me making sense of this. Y values are positions. And now instead of like the derivative function, the slope values are the velocities. So that's just kind of how you calibrate your brain for the problem. Okay, so where are the slopes less than 0? Well, that's where the graph is going downhill. So it's here and there. So let's go ahead and write the intervals up here where I can see it, and then I'll paste it down there. So the open intervals are going to be t epsilon, parentheses, 2 to 4, union 6 to 7, and then we'll go ahead and put seconds at the end. Is everyone okay with that? Now, because it said open intervals, we don't have to worry about, putting brackets at all. We'll just do what they say, because sometimes, there are some professors where they put brackets around their intervals. But we're going to do open intervals. Now, it said to justify. Is this enough justification just to say on these intervals v of t is less than 0? Not quite, because what's v of t? Have we said it? No, they gave us y of t. So if you start throwing out these b's, no one's going to know if you're talking about like Velveeta cheese or something else, right? So there's a couple of ways to do this. You can either make one blanket statement up here, like I like blankets, or let v of t be the slopes of y of t. If you say that up here one time, now when you refer to v of t being negative down below, that's good, because now we're like, oh, that means the slopes are negative. Okay? Otherwise, you have to say this. You'll say, these are the intervals, and then the justification would be, since on these intervals, then you would just say it here, the slopes of, would you say the slopes of the graph? Would that work? The slopes of the graph? The graph of the function, would that be any better? No, neither one of those are good. You could say the graph of y of t, but you don't even need to say the graph of. Just say the slopes of y of t are negative. Okay? Or you could say, since on these intervals, y of t is decreasing. I would say the same thing. All right, so you always want to relate it specifically in your justification to what is given. To what is given. We're given the graph of y, so we have to show or explain how we're using that graph to justify or to get our answer. Okay, next one. On what open intervals from 0 to 7 is the particle at rest? Particle at rest. So again, in your head, here's what you're thinking. v of t is equal to what? 0. So that's kind of a mental setup, like up here, v of t was less than 0. And of course now, v of t are the slopes. So we want to know where the slopes are 0. Now we have something to look for. It's going to be on the interval from 0 to 2. So we'll just say over here, 0 to 2, t epsilon, 0 to 2 seconds, comma, since the slopes of y of t are 0 on this interval. And again, that's a judicious use of a pronoun. This refers clearly back to my answer. Now, if we had made that statement at the top, that v of t are the slopes of y of t, then you could have just said here, since v of t equals 0 on this interval. Okay? It's kind of like a map legend or whatever they call it, where it defines what some of the things are. You could do that one time or just write it every time. Part C, at what times from 0 to 7 open interval does the particle change direction? At what times does it change direction? So again, in your head, you're thinking, okay, we want v of t to do what? Good, to change signs. Remember, it doesn't necessarily have to happen by passing through 0. We can have non-continuous functions that do that. We want v of t to change signs. Well, v of t are the slopes. So I want the slopes to change signs. Now at 2, there's the first one. Does the slope change signs at 2? Actually, no, right? Because 0 has no sign. It goes from 0 to negative. If you think about it, the particle is at rest for the first 2 seconds, and then it begins moving. So that's not changing directions. But what about at 4? The slopes change signs. At 6, the slopes change signs. Now remember what I said also, that we have to talk about how the signs change. We can't just say that they change signs. Those change signs in different manners, right? So we have to justify each of those separately. Wow. So this is where it gets a little bit of writing. So let's go ahead and say at t equals 4 seconds and t equals 6 seconds, comma, since, you can still answer them in the same question, since the slopes of v of t, the slopes of y of t change from, and we'll just kind of go from left to right. We listed the 4 first. So at 4, the slopes change from negative to positive, and then from positive to negative. Actually, we could put them in there. The slopes change from negative to positive. I was going to do respectively, but it makes better sense to say at. Negative to positive at x equals 4 seconds, and positive to negative at x equals 6 seconds. Now, if you wanted to say negative to positive and then positive to negative at x equals 4 and 6, then you would probably want to add the word respectively at the end. But this makes more sense. So we still did it in one sentence, but we had to justify each of them separately. You could do it in 2 sentences if you want. At t equals 4, since at this point the slopes of y change from negative to positive, and blah, blah, blah. All right, last one maybe before the bell catches us. 30 minutes goes by fast when we're doing math, doesn't it? I guess I need to take that down there. Okay, during the first 6 seconds, what's the particle's displacement during the first 6 seconds? All right, so how do we find displacement? Yeah, endpoint minus start point. So during the first 6 seconds, that's going to be where it ended up at 6, that's y of 6, minus where it started, y of 0. And so there's your setup. There's your your setup. Now all we have to do is get those values from the table. Y of 6 is 0, and y of 0 is 6. So that equals -6. And what are the units? Inches. All right, so the last thing here before we call it a day, explain what this means in terms of the particle's change in position. All right, so here's the sentence. During the first 6 seconds, the particle is, we could just say displaced. Positive or -6 inches? Positive 6 inches, and then we interpret it where? Above, below, left, or right? Yeah, this is where it's important to remember that we're on a vertical line. Displaced 6 inches below its starting position. Starting position. All right, particle motion, we're done for the day. We've got a couple more to go in here, and then we'll move on to the next section, which is really fun. One of my favorite derivative rules, the chain rule. Chain, chain, chain.